All right, so today we are going to be talking about calculating pH of different types of acids and bases. So you should have a calculator. You should have your in-class problems out. Okay. So let's review a little bit of stuff from last class. Hold off on answering. What is the main difference between an acid that is strong or a base that is strong? Let me rephrase that. What is the main difference between an acid or base that is strong and an acid or base that is weak? What do we think? Yes. Not the concentration.
How they dissociate.
Can you be more specific?
Strong acids completely dissociate.
So the amount that they dissociate in water is what you're getting at, right? So the concentration, you can have an acid, you can have a weak acid and a strong acid that are at the same concentration. Their pHs are going to be different, though, because it has to do with how much it's dissociating in water. And as you started to say, strong acids and strong bases do what in water? Completely dissociate. They have 100% dissociation. And weak acids and weak bases only partially dissociate. Remember that from last class? And that's the main difference between strong and weak. Okay? Is their amount of dissociation in water. So, when we are finding the pH of a strong acid or a strong base, all we need is the concentration of that acid or base because there is a 100% dissociation. To recall from last class, to calculate pH, you need the concentration of what ion? H plus or H3O plus. We can use those terms interchangeably in this class. Some classes, they do talk about the difference. For us, they're the same thing, okay? For most chemistry, they're the exact same thing. All right, so just remember pH is negative log of H plus concentration. So, for strong substances, there is a 100% dissociation. Or you can also say that there's a complete conversion of the weak acid or weak base to its ions. So let's look at HCl. HCl, that is a strong acid. It completely dissociates into H plus and Cl minus. 100% dissociation, 100% conversion. So it becomes a stoichiometric problem here. So the concentration of HCl, the 0.450 molar, that is completely converting into H plus and Cl minus. It's like in Unit 2 when we were talking about finding concentration of ions for an ionic compound. You just took the initial concentration and multiplied by the coefficient on the ions. But that only works when it's 100% conversion. In terms of equilibrium, the equilibrium constant for strong acids and strong bases is ginormous. It is huge. It is so much greater than 1. All right? We are pretty much driving towards the right. The products are what you're going to have mainly in solution. You're not going to have really any of the HCl still together at equilibrium. Okay? So to find the pH of this solution, all we need to do is take negative log of the initial concentration because it is the same as H plus. So pH is going to be negative log of 0.450. Let's review a few things. What units does pH have? There are no units. How many sig figs does our concentration have here? 3. So how are we going to represent 3 sig figs in our pH? 3 digits after the decimal. Okay? So go ahead and calculate that pH. Yeah? Yep, 0.347. Cool? What do you notice about this next problem, number 8? It's a base. Can you be more specific? It's a strong base because it's a group 1 metal with hydroxide. All right, so since this is a base, let's write out that equilibrium, or not equilibrium, let's write out that dissociation equation. What are the ions that this will break up into? K plus and OH minus. And since this is strong, the concentration of KOH, the 0.710 molar, is the same as the concentration of both ions, because there's that complete conversion. So in order to find pH, wait, but my reaction doesn't have H plus in it, so how am I going to find pH? I can find POH from the hydroxide ion concentration and then subtract POH from 14 to get pH. Is that the only way I can find pH? No, you can use that KW formula, go from OH minus to H plus, and then do negative log of H plus. Knowing that there's multiple avenues to approach these problems is beneficial, because sometimes, depending upon what you're given, you have to be able to get to the right answer various ways. Okay? I like subtracting from 14 as much as possible. So if we do, if we find POH, we're going to do negative log of 0.710. So what do you get as your POH? Yep, 0.149. That maintains proper sig figs. And then we'll subtract that from 14. To get our pH, which would be what? Yep, 13.851. Yeah. So let's look back at our two answers for these problems. Do our pH answers make sense for what the substances are? Yeah. For our first one, our pH was 0.347. That's very acidic, which makes sense because this is an acid. This pH is very basic for the second problem, which makes sense because it's a base. Cool? That should be real easy. That's like the, if you know, in first year chem, that's probably what you had to do in terms of finding pH of acids and bases, was this type of stuff. It was always strong. You didn't really talk too much, depending upon where you took first year chem. You probably didn't talk much about weak acids and weak bases, other than if it's not strong, it's weak. Okay? Well, this year we were going more in depth. So let's talk about some weak acids and weak bases. All right. So for number 9, we are going to calculate the, actually, let me back up a little bit. Getting ahead of myself. When we are finding the pH of weak acids and weak bases, there's not a 100% conversion. There's not a 100% dissociation of that weak substance into its ions. It's only a partial dissociation. So it's not going to be just the negative log of the initial concentration, because not all of it is being converted into the ions. So instead, we're going to have to use a Rice table. Okay? I know. Oh, that sucks. Well, the name of this unit is acid-base. No, the name of this unit is not acid-base Rice. The name of this unit is acid-base equilibrium, so Rice tables are not going away. Our reaction for our Rice tables for these acid and base problems will always be the Bronsted-Lowry reaction of the weak acid or weak base with water. Kind of like what we were writing in number 6 at the end of last class, where we left off last class. Okay? So let's look at this first problem. We're going to calculate the magnitude of the equilibrium constant for benzoic acid, and I give you the formula. If a 0.100 molar solution has a pH of 2.59. All right, so let's start to unpack this problem a little bit. Let's write our reaction. So HC7H5O2, we're going to react that with water. Now, which of these substances in the reaction is acting as my acid? Benzoic acid. There's several ways that you know that benzoic acid is an acid. You should know it from the name of it, because it says acid. But what if you didn't know? Like, what if the problem was worded as, oh, a substance, here's the formula, blah, 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 blah. It didn't tell you the name of it. How would you know from the formula that it's an acid? It begins with H, right? What if you didn't know, like what if it just said some unknown substance and you didn't know the formula? How could you know it's an acid? But how do you know that? Because of the pH. Notice that the pH is less than 7. So that means that this solution is acidic. Now, how do we know that this is a weak acid? Other than the fact that we're doing pH of weak acids and bases, how do we know this is a weak acid? It's an organic acid. It's got that carbon. Again, what if you didn't know the formula of it? How would you know it's a weak acid? Okay, I'm not going to be asking you for the equilibrium constant of a strong acid or base. That's a good way to know. Also, let's treat this for a moment as if it were a strong acid. What would the pH be if it were a strong acid? What would it be? Can we calculate it? Yeah, wouldn't it just be negative log of 0.1 of the concentration? What is negative log of 0.1? If you need to calculate it, that's okay. Yeah, it's not 2.59. This is true. It's 1. So the fact that this pH is higher means that not all of my original substance is converting over into its ions. See all these different ways of recognizing what type of problem you're being given. Okay, and depending upon the problem, you might need to use one or more of those tools to know how to approach the problem. Because that's what I'm teaching you. I'm not teaching you how to do this particular problem. I'm teaching you how to do any type of acid-base problem given the problem, given the information. Okay, so I'm trying to show you different ways to approach them. Okay. So we know that benzoic acid is my acid for all the reasons we previously mentioned. Therefore, what's water? My base. And in Bronsted-Lowry reactions, we have a transfer of a proton or hydrogen ion from the acid to the base. It always goes A to B. So think alphabetical order. So A to B. Which of those hydrogens is benzoic acid going to give up? The first one, typically, yeah. So my products are going to be C7H5O2- and H3O+. Exactly. All right. Let's start filling in the information we know. What is my initial concentration of benzoic acid? 0.100. What state of matter is water in? Liquids. We can actually just cross it out. We don't care about the amount of water because its amount will not affect the equilibrium. It's still part of the reaction, but it doesn't matter for the equilibrium position. Okay? You're going to like that part of acid-base equilibrium because you can always cross off water. And what do you notice about this reaction in terms of its balancing? It's 1-to-1. Most of our acid-base reactions are going to be 1-to-1. You're also going to like that part. Makes it real nice and easy, right? All right, what are our initial concentrations of my products? 0. Not until about halfway through this unit, when we switch over to chapter 15, are we going to have initial concentrations for our products that are going to be something other than 0. So not yet. Let's start with the basics right now, or the acidics. Okay. pH is always at equilibrium. So whenever you're either given pH or you're asked to solve for pH, it's always when that reaction is at equilibrium. Okay. All right, so which direction will this reaction proceed? It's going to proceed towards the right because we have none of our products. So therefore, what's my change for my reactant? Minus X. And what about my products? Plus X for both. So this is X, And this is 0.100 minus x. Okay? All right. Let's write the equilibrium expression, and then we'll talk about how we're going to solve for the equilibrium constant. So what's the letter we use for equilibrium constant? K, right? What subscript are we going to give this? Why are we going to give it a subscript of A? Because it's an acid. See how that works? And that's going to equal the concentration of C7H5O2 minus times H3O plus all over HC7H5O2. Yes? All right. You can toss it back up here now. Yeah. Okay. Now, we are told that at equilibrium, even though it doesn't specifically state at equilibrium, but at equilibrium the pH is 2.59. Okay. Again, whenever you see the words pH, it's always you should imply that that means, or you can infer that that means it's at equilibrium. So the pH is 2.59. Now, the pH is going, we're trying to solve for Ka. We don't know Ka. So we need to know some other things, right? So 2.59 is going to help me get to what concentration at equilibrium? What equilibrium concentration is that going to tell me? Is it going to help me get to the equilibrium concentration of benzoic acid? Or of benzoate ion? Or of H3O plus ion? H3O plus ion. pH will always help you get to H3O plus ion. Okay? So we're going to use the pH to calculate the equilibrium concentration of hydronium. How do we go from pH to hydronium ion concentration? 10 to the negative pH. Because remember, hydronium and H plus we're using them interchangeably. So H3O plus concentration is equal to 10 to the negative pH. Okay. And in this case, X equals my hydronium ion concentration. So X is equal to 10 to the negative 2.59. How many sig figs does that pH have? 2, because we're looking at the number of the digits after the decimal. So when we do 10 to the negative 2.59, report that with 2 sig figs. And what do you get? 0.0026. So now we know X, we can plug that in for everything else, right? So Ka is 0.0026 squared over 0.100 minus 0.0026. Because this is, x squared over 0.1 minus x. And I'm plugging in for x. Yeah? This should be really easy. I'm assuming that the looks I'm getting right now are because this is really easy. And what do you get as your Ka? I'm sorry, what was your exponent? Yes. Yep, 6.9 times 10 to the negative 5. Now, does that answer make sense? This is a weak acid, right? You guys told me that before. Should weak acids have Ka values less than 1? Yes, because they're only partially dissociating. Oftentimes, weak acids and weak bases have less than 5% dissociation. Very small amount of it is dissociating. So they're going to have very small Ka values. Okay? All of our weak acids and bases that we're going to be working with have Ka and Kb values smaller than 1. Strong acids and bases have Ka and Kb values greater than 1. See how that works? Okay, cool? How do we feel? You want to do another one? Let's do another one. Take a moment to read this problem to yourself. All right, let's set up the rice table. What are my reactants? NH3 and H2O. Now, how did I know that I need to do a rice table? If I'm doing a rice table, it implies that this substance is what? Weak. It implies that it's weak. You're not going to do a rice table for something that's strong. Okay. So how do I know that this is weak? How do I know that ammonia is weak?
Because ammonia is weak. That's one of the things we're doing.
Okay, that was something I told you, just to know that ammonia is weak. What if, again, what if this was like some unknown substance? How would I know that this solution was weak, given the other information in the problem? If I do negative log of this, yeah, we're not going to get a pH of 11.13. We would get a pH of 13, right? How do I know that this is basic? Because the pH is greater than 1, right? Or greater than 7. The pH is greater than 7, so therefore we know that this substance is basic. We know it's weak because NH3 is ammonia, and ammonia is used so frequently, we just know it's weak. But more importantly, applying it, if we assumed it was strong, we would calculate a pH of 13, not of 11.13. Got it? Okay. So since we know that NH3 is a weak base, what are going to be my products of this reaction? Exactly. NH4 plus and OH minus. Cool? All right, so let's start plugging in the information we know. What am I going to do next? Cross out the water. Sorry, water. We love you. You're very important to us, but not for our equilibrium, right? What's my initial for NH3? 0.1. What are my initials for my products? 0. Yep. For a while, it's going to be 0. Okay. All right, so which way will this reaction proceed? To the right. So this is going to be minus X. It's a 0, not a 6. Cool? All right, so let's write out the equilibrium expression. So I'm going to write a K expression. What's going to be my subscript here? B, because this is basic. NH4 plus times OH minus over NH3. All right. So KB is equal to x squared over 0.1 minus x. Yeah? All right, now I need to find x. What information am I going to use to solve for x? The pH. Now the pH is going to get me the H plus concentration, but how is that going to help me here? Because this reaction doesn't have H plus. Because I need to find OH minus concentration. I need to find that because that's going to be my X. So find POH and then find OH minus concentration. All of your acid-base reactions, all of your weak acid, weak base reactions will have either H3O plus or OH minus as a product. and your pH will get you to those, or those will get you to your pH. Okay? Always. So if pH is 11.13, what is our POH? 2.87. And then so we can find OH minus concentration by doing 10 to the negative 2.87. Yeah? Yeah. Yeah. So what is our hydroxide ion concentration? Yep. Which is our X. So now we can plug in, right? So Kb equals 0.0013 squared over 0.100 minus 0.0013. Cool? Go ahead and calculate that. And what do you get? 1.7 times 10 to the negative 5. Got it? So these two problems where we're asking you to solve for the equilibrium constant given the pH and the initial concentration. What if I gave you the initial concentration and the equilibrium constant, and now you need to find pH? Yeah, that's what we're about to do. That's a good assumption to make. What? No, the world does not end. Sorry. So you guys ready to do those problems? Okay. I don't know why it keeps cutting off. I know why. I just keep forgetting that it does this, where it cuts off. Okay. So we're going to calculate the pH of a solution, which is 0.712 molar CH3NH2, which the official name of that is methylamine. And we're given the Kb is 4.4 times 10 to the negative 4. So what are we going to have to do? Okay, well, we're going to have to set up a rice table. All right, so my reaction is going to be CH3NH2 reacting with water. Okay. Which one of those is going to be acting as my acid? How do you know? Notice that we're given the Kb of this substance. We're given the Kb of methylamine. That means methylamine is a base because you're given Kb of it. See how that works? All right. So that means methylamine has to be my base, water has to be my acid. So knowing that, what are my products? NH3 plus and okay. My E is like really tall. You can still cross off water because it's still going to be a liquid. Like the setting up of the rice table is going to be the same. So methylamine's concentration is 0.712. These are both 0 until we get to chapter 15. Then we'll have more information given in the problem, knowing if we have some of those. What's my change for methylamine? Minus X. And what's my change for my products? Plus X, X, 0.712 minus X. All right, well, you know what? Let's before I talk about a few things that will hopefully make your life easier, let's write our equilibrium expression. Okay? So we have Kb equals CH3NH3 plus times OH minus all over CH3NH2. Let's go ahead and plug in the stuff we know, right? So we have 4.4 times 10 to the negative 4 equals x squared over 0.712 minus x. All right, in general, relative, how much do weak acids and weak bases dissociate? Not a lot, right? A lot of them are less than 5%. Some of them are still greater than 5%, but yeah, not a lot. So little, in fact, that this minus, oh, I don't want to use that color, that this minus x oftentimes can be omitted, can be negligible. And that minus x becomes negligible. Meaning, because we're starting off with 0.712, if it's dissociating less than 5%, the amount that it's dissociating is so small that your equilibrium concentration is going to be barely different from your initial, that it's not going to affect the overall mass, not really. Okay, now this x, these x's here will always, what's the opposite of negligible? I don't know what that word. Yeah, these will always not be negligible. These will always be important. Significant, yeah, I guess that's a good way to say it. These will always be significant because we're starting with nothing becoming something. Okay? What? That's written. Eligible? No, that doesn't work. Yeah, unnegligible. Important. Significant. Now, your textbook walks you through a process of using, it's called the 5% rule. It says, solve the problem considering that minus x to be negligible, to omit it. And then if x, hey guys, can you pay attention over here? And then if your x that you solve for is less than 5% of the initial concentration, then you're good. But if it ends up being more than 5%, you then have to go back and redo the problem. So let me show you another way to figure out if that minus x is negligible before you even solve for x. Okay? So, initial minus x. This is negligible when, so you're going to take your initial concentration of your acid or base and divide it by the K value given in the problem. If that is greater than 400, then it's negligible. Okay. This formula was derived from the 5% rule. It just, had to go a different way. This is an easy check before you even solve for x if you can get rid of that minus x to begin with. Okay. So let's practice with this one. We have 0.712, and we're going to divide that by 4.4 times 10 to the negative 4. Go ahead and do that. And what do you get? Yeah, like 16, 18. And then it's like point something, 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 something. Okay. Is that greater than 400? Yeah. Okay. So therefore, we can omit that. The minus x. So then it just becomes x squared over 0.712. If we couldn't omit that, then you have to do like the graphing both sides, or you have to do the quadratic formula or whatever to find your positive x. Which you can still certainly do for these problems. You can be like, you know what? I don't care that it's negligible. I don't care that that number's so small. I'm still going to account for it. It's just adding extra stress and time for you. Okay? Yesterday in third block, we did it both ways, and we found that it only changed your pH, your final pH, in the thousandths place by 3 points. It's not enough to make a difference. Okay? Cool. All right, so now let's finish out the problem. So now that we have 4.4 times 10 to the negative 4 equals x squared over 0.712, what's x? What'd you get? I got 0.0177. Yep, practically the same thing. I'm basing my sig figs off of my initial concentration, not the K value. Because the K value is a constant, so we can ignore its sig fig. So all we really care about is the initial concentration. Now, are we done with the problem? Nope, because what did it ask me to solve? pH. What do I have right now? I have the concentration of OH minus. So now I need to find pH from that. Now, I'm not going to be checking for your work on that. Okay? You don't have, and the AP exam, if you, like, X is this, identify that that's OH minus concentration, and then you can be like pH equals, and then the right answer. You don't have to show those individual steps. I'm going to write them down because this is our first time doing this problem. Okay? So we're going to take the negative log of 0.0177, and that's going to get me the POH, which is what? I actually don't have it written down. What is it? 1.752? 1.752, and then 14 minus 1.752 will equal my pH, which is? And that's the answer. Does that answer make sense for the substance? Yeah, it's basic, so the pH should be greater than 7, right? The initial concentration, always. Yeah, so my initial concentration was 3 sig figs, so I need to have 3 digits after the decimal in my pH. Yep. And if you had gone through here, and if you didn't omit that minus X, I believe the answer was 12.243, which is like 0.005 away. It's practically the same thing. That's within the margin of error. As long as your calculated pH is within 0.5 pH units of what it's supposed to be, you're good. Yeah, like around 0.5. You get it, but it's actually, it's not that huge of a margin. Because it's, remember, pH is a inverse log base or negative log base scale. So it's, yeah, it's not that, it's not even off by a factor of a power of 10 away. So as long as you get really close, you're good. Okay? Ready to do another one? Yeah, you're excited. I can tell. You know what? Let me let you guys tackle this problem on your own. I'm going to pause it while you do that. So we have pyridine, so rice. This is a base because it's Kb. So therefore my products are C5H5NH plus and what? OH minus. Good. So we're going to get rid of water. C5H5N is starting off as 0.10. My products are both 0 to begin with, so that's going to be plus X minus X. 0.10 minus X, X, X. Whew. Okay, so we're going to write the Kb expression. C5H5NH plus times OH minus over C5H5N. Okay, so can we omit that minus X? Did you check it? You did 0.1 over the KB. Yeah, way greater than 400, right? So yes, we can omit that, right? Or we can say it's negligible, however you want to say it. So 1.7 times 10 to the negative 9 equals x squared over 0.10. Right? So when you do that math, what do you get for your x? 1.3 times 10 to the negative 5, right? Now, this problem did not ask me to find pH. If it did, then I would do negative log of the x and then 14 minus that to get to the pH. Instead, it asked me to basically figure out what is the percent dissociation of my weak base, of my pyridine. Okay? So x is equal to the concentration of both pyridinium ion and hydroxide. But I don't care about the hydroxide. I only care about the pyridinium because I'm trying to find the percent dissociation. The percent dissociation is going to be the concentration of C5H5NH plus that is formed from the initial C5H5N. Okay. For this math, it doesn't matter if you put initial or equilibrium for the C5H5N on the bottom because they're the same mathematical value, right? They're both 0.1 because we said that the minus x was negligible. So percent dissociation, we're going to have 1.3 times 10 to the negative 5 over 0.10 times 100, which is? Yep, a very small percentage, way less than 5%, which is why when you did initial over KB, it was way greater than 400. Yeah? Cool? You got one more problem in ya? Well, we have like 15 minutes left of class. We have until the 41. How about we do the last problem so we're at least on track with the other two blocks? Yeah, exactly. Where's my foam cube? Do you still have it? Okay. Just want to make sure that you guys didn't steal it. Okay, so this problem. So this problem, we have an acid, HX, is 25% dissociated in water. And we're told that the equilibrium concentration of HX is 0.30. Calculate the Ka value of HX. All right. Tell me what you know from this problem about HX. It's an acid. Good. Okay. What type of acid is it? It's a weak acid. So it's a weak acid. We know that for two reasons. I'm asking you to calculate Ka. I'm not going to ask you to calculate Ka for a strong acid. And it's less than 100% dissociation. It's only a partial dissociation. Got it? Good. So we're going to write a rice table, right? Oh, I'm not on the pen. We're going to write a rice table. So HX plus H2O. If HX is an acid, what are my products of this reaction? H3O plus and X minus, right? Xe is xenon. X, we don't know what it is. It's an unknown, it's just a random acid HX. Get rid of the H2O. Good thing you get a periodic table. Too bad your periodic table doesn't have names. All right. So, cross off H2O. Yeah, Wolfram. All right, HX, what's its initial concentration? No, 0.30 is the equilibrium concentration. We don't know the initial concentration. No, it's not 0. We don't know it. Another variable, let's call that Y. Q? Okay, well, you can put Q on your paper. I'm going to put Y up here. What are my initial concentrations for H3O plus and X minus? 0 and 0. Therefore, which way is this reaction proceeding? Right. To the right. So plus X, 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 minus X. Is that minus X, is the amount that HX is changing by negligible or not? We do know if 25% is a substantial amount. Remember, it has to be less than 5% dissociation for it to be negligible. This is 25. This is 5 times that. So this minus X is a significant amount of the initial concentration. Okay? So, in order to, let's write our Ka expression. Ka is H3O plus times X minus over Hx. We are trying to find Ka. Right now we have too many variables. We have y, we have x, we have Ka. So we're going to have to use some information given to get rid of some of those variables. Hopefully we can solve for both y and x, or actually we really only need to solve for x. There is a way to only solve for x. I like solving for y first and then finding x. Okay, I like finding that initial concentration first. Okay, what do we know about that initial concentration? What do we know it's happening to it? 25% of it is going to dissociate. So we know that X is 25% of Y. Right? That's still two variables though. So what's another way we could say? Or we could say that 0.30 is 75% of y. Right? Now you technically, since we have two formulas here, you could solve directly for x and not ever find y. But my brain doesn't work that way. Your brain might work that way. For me, I'm like, you know what, let me find y first and then subtract to find x. But you could be, I don't want to say students' names because this is recorded, but you can be like a student who sits in that seat during 6th block who also goes to the same school as you and you and you. Shh! No names. Okay. So, if 0.3 is 75% of y, then I can take 0.30 and divide it by 0.75 to get y. Right? I'm just math, doing algebra here. What is that? Therefore, y is 0.40. Yeah? And therefore, x is 0.1, because we know that 0.40 minus x has to be 0.30, so therefore x is 0.10. Woo, yay math. All right, so now I can plug everything in. Ka is equal to 0.10 squared over 0.30. What do you get? That is a relatively large K value. Like for a weak acid, that's fairly close to 1. Considering weak acid, weak bases, the ones we were doing previous to this were like 10 to the -5th, 10 to the -9, 10 to the -4. Like they were much smaller. This is really close to 1, which makes sense because it's 25% dissociation. The more it dissociates, the larger the K value. Cool? All right, that's it for today.